Alright, so we're going to get started here. Again, apologies for having to shift the time. I had another meeting that I had to be in attendance for, but we'll be back to 1 o'clock next week. So we're taking a look at the section 4.5, connecting variation, rate of change, and first differences. So little quick recall on some of that. We have the two different types of variation. There's direct, which has us looking at an equation something like this, y equals kx, where k is the rate of change. Your graph would pass through 0. Okay, so this is the important part, that it passes through the 0 here. In the case of partial variation, then you're looking at a graph, or an equation, sorry, something like this, y equals kx plus b or something, where again the k is still your rate of change, but your b is the initial value. That's the starting point of the graph. So it just means that the graph is not going to start at 0. So you might have something that looks like this. It starts up here. Again, the key being that its starting point is on the 0 axis. Here, the y-axis, it's not touching 0 on the x, and might be looking something like this. So this could be y equals 5x as an equation, and this could be y equals 3x plus 2, something like that. And again, these graphs could go downwards as well if the rate of change was negative. And again, the rate of change is how much you're going up and down on those kind of steps you make with the rate triangle. So that's your rise over your run. So in this case, for every 1 you rise up, you would run over 5. Here, the idea would be that for every 1 you rise up, you run over 3. And it's negative if you're going down in your rise, because again, we read from left to right. And then the first differences portion, that's when we're working on the tables, and we'll take a look at that right away in question number 2 there. We'll kind of review that. So we'll take a look at a couple of these questions. Again, if you have any questions along the way, shoot me a message in the live chat or Edsby or email, and I'll try and answer them. Again, you can do that outside of the live streams as well if you have questions. But let's take a look at some of these questions. So we'll start with, we had 1, 2, 3, 4, 8, and 9. So let's take a look at question number 1. So in question number 1, what we're looking for here is the initial value and the rate of change. And in each case, we're given an equation, and that equation, then we can just use that idea that these are going to be either a direct variation or a partial variation, and we can compare those to those examples we just did on in the intro there. So in the first case, I have I equals 20 plus 5 or 15t, and it says that gives the internal temperature I in degrees Celsius of a 10 kilogram turkey being roasted for t hours. So this is the increase in temperature of a turkey internally. So if I switch over to that one, so here's my equation. So the initial value and rate of change is what we're looking for. And so again, this is looking like the partial variation, other than our variable, our x variable, in this case a t, is just at the end. But it's still, this is our initial value, call it IV, and this is our RC, or rate of change. So that easily picks those out. So 20 and then plus 15 are the two values. And note that I did say plus 15 because that positive sign does connect with the rate of change. The temperature is going up, meaning this graph is going to slope up, similar to the examples here. In the next case, we are given the situation where H equals 20 or 2000 minus 5.5t, which gives the altitude h in meters of a parachutist t seconds after opening the chute. So this guy, someone's parachuting out of an airplane or whatnot, and they're going down. Thus, we should have a graph that's decreasing. So rate of change should be a negative number. So right away, I can look at that equation and recognize where the rate of change is by the negative sign, the negative 5.5t. Also, that it's the number connected with the variable. So here, again, this is our rate of change. Negative 5.5 is our rate of change. Okay? And again, I'm including that sign. And then the 20,000, that is our initial value. And depending on who's writing the equation, you'll notice so far we have these written where the initial value is first and then the rate of change portion. I tend to write it this way, and I was taught to write the rate of change first and then the initial value. And a lot of your teachers, I know at the school, will do the same thing, and they'll call it y equals m instead of k, x plus b. And they'll use it in that format. But it doesn't matter which order they're in. It's always the case where the rate of change is connected to the letter, and then the number by itself would be the initial value. All right, so looking at the next one here, we have C equals 2 plus 1.5D, which gives the cost, C in dollars, of a taxi ride of D kilometers. So again, this is laid out with that number first and then the variable portion coming at the end. And so here we have it. The 2 again would be our initial value. Circle that, I don't know. And then this here, the plus 1.5, would be the rate of change. And again, to reiterate, don't assume that the first number is always going to be the initial value and the second is going to be the rate of change, because it could be written either way. Like I said, over here, this is the initial value, and this part's the rate of change. So it doesn't matter which order they're written in, as long as the number connected to the letter is the rate of change. The other value will be your initial value. In the last case, it's going to be slightly different. It's a little trick here if you were getting comfortable with that setup. So what we have here is 5,000 times 0.02 times t, or sorry, 500. I wrote 5,000. 500 times 0.02 times t. And so in this case, there's no plus or minus sign. And actually what we can do is we can simplify that equation. Anyways, just to describe it, I guess, it is the interest paid on $500 investment at 2% interest rate after 2 years. So this is actually based on the simple interest formula. If you collect interest and there's no what's called compounding on it, which is what we generally get if we're taking out a loan from a bank or using our credit cards and they charge you interest, they actually are going to charge you interest and then you'll pay interest on the interest. In this case here, you're just paying interest on $500 alone. So in that case, what we have here, we can simplify this, and I'm going to rewrite it out. This is A equals, and now this is 500 times 0.02, or 2% of 500, and so we can actually simplify this down to 10t. And oh, my camera's frozen. Hold on a second. There we go. Fixed it. Okay. So yeah, this simplifies down to 10t. We actually multiply that out. We get 10t. There is no portion that is being added here, so there is no initial value. So the initial value in this case is not there, or because this would be a direct variation, the initial value would be 0. So the IV is 0. I'll use a little line there to note that it's 0, not the number, not O. So do be careful. Again, we might have, this is one where you could have got stuck in that thought process of, oh, this is the initial value because it's first, and then there's the rate of change, but it's not, because this is actually multiplied together, not added or subtracted. So they are separated by an addition or subtraction sign when you're looking at the rate of change in initial value. Okay, moving on to number 2 here. In number 2, we are looking at the table of values that has Abby records the height of a plant each day for 5 days. What does the table show you in relation to between the height and the day? And so we have a multiple choice type of question here. We're looking to see if it's linear, not linear, if there's a constant rate of change, or if it has a decreasing rate of change. So as we go through each day here, we're going day 1, 0, 1, 2, 3, 4. The initial height was 4 centimeters, and then it goes up by 1 centimeter, then it goes up by 2 centimeters, then it goes up by 3 centimeters, then it goes up by 4 centimeters. So the rate of change is not constant. It's changing all the time. So it's definitely not C. It is going up, so we're not decreasing. So the question then becomes, is it linear or not non-linear? And because it's not constant rate of change, and it's a different rate of change every day, it can't be a linear equation. A linear equation has to have a constant rate of change. It has to go up by the same amount each day, or each time in this case is days, but every step has to be the same size. In this case, it's getting bigger and bigger and bigger each time. So it's not constant. Thus, the answer to 2 is B. Now, like I said, I was going to get to the first differences. Best way to do it is do a table. So since we have a question with a table of values, we can do this one. So we're asked to copy and complete the table, determine if it's linear or nonlinear, and then describe how the first differences are related to Tammy's rate of pay. Now, note rate of pay would be the rate of change as well. In this case, it's the rate of change, the changes in her pay. So if we take a look at this question, what we have is I have the table kind of quickly drawn out here. So her hours go 5, 10, 15, 20, 25. And then she was paid $12.50 an hour. So we multiply that by the number of hours she worked in any case. So $12.50 times 5 is going to get you $62.50 for 5 hours. And then each time we just multiply 10 by $12.50, we're going to get $125, bang on. Then 15 times $12.50 is going to get us $187.50. And then 20 times $12.50 is going to get us $250, right on the nose. And then finally 25 hours, she's going to get paid $312.50. So there is the table of values filled out, and now we need to do the first differences. So recall the differences is the calculation of how much are we going up or down each time. So this number here, subtract this number here. So 125 minus 62.50 is going to give us 62.50. And then the next one ends up being the same if we subtract them. And in each case, as we subtract these, all these values end up being 62.50. And if you want to check them, again, 187.50 minus 125, 250 minus 87.50 is right there, and then $312.50 minus 250 is that one right there. So our first differences are the same, and because the first difference is the same, that means that we have a linear relationship. So that was part B. So the first differences are the same or constant. Could be another term you could use there. And then in part C, it says, describe how the first differences are related to her rate of pay. Well, her first differences here are 62.50, 62.50, 62.50. That's how much she got paid for 5 hours. How is it related? Well, she gets paid $12.50 an hour, and this is just 5 times that because her hours were going up by 5, so this went up 5 times as fast. So the first difference goes up 5 times as fast as the pay. And generally, we like to look at the first differences as being going up every individual hour, but in this case we were given every 5 hours. So in that situation then we have the first difference is going up quicker, and so it's not just the rate of change, but it's 5 times the rate of change. So as long as these numbers here in our hours column are going up by the same amount, we are able to calculate that. If these weren't going up by the same amount, if we had like 1, 10, 20, and they're jumping around a bit like that, they're not going up by the same value, then we have an issue and we can't calculate the first differences using this method here. Okay, so number 4 is next, and in question number 4, it says that an equation T equals 10 plus 5m represents the temperature T of a pot of water in degrees Celsius T minutes after it is placed on a stove. Represent this relation and the rate of change in 3 ways: in words, in a table of values, and graphically. So this equation here is a partial variation because the initial value does start at 10, so the temperature of the water in the pot would have been 10 degrees when it came out of the tap or wherever it came out of to be put in the pot. So it initially starts at 10 degrees, and then it's going up 5 degrees every minute. And so in words, that's what we could state: the initial temperature, and then how much it's going up per minute. So the initial temperature is 10 degrees Celsius, I believe it was. So the initial temperature is 10 degrees Celsius, and it increases. And this is important that we note that it increases or goes up as opposed to decreasing or going down, because then we'd have a temperature that's cooling off. So there we are. The initial temperature is 10 degrees, and it increases by 5 degrees Celsius each minute. And there it is, an I there, not 2 M's. The next portion here has us describe the relationship with a table of values. And so here we have a table of values. I figured 0 to 5 would be some good numbers for the time, and it will illustrate enough information for us. So it starts at 10 degrees Celsius, and it goes up by 5 degrees each minute. So 10, 15, 20, 25, 30, and 35 is our final value there. And again, the other way to calculate that, if you didn't have this statement here, is that you just use your formula, and each time the 10 portion here, that comes from T equals 10 plus 5 times 0. And I just got the 0 from there. The next one would be T equals 10 plus 5 times 1. And again, you just use these in each of these m's to find the respective T value. And again, you get to pick the m values. You get to pick the first column the x value column. In this case, I felt, again, going up by a minute made sense for our purposes. And so you fill in each of those t values based on the m values that you picked here. Generally, it's good to pick about 6 values when you're doing these types of questions. And now, how does that relate to the rate of change as well as what it asked in that table of values? And what we could do is we could actually calculate the first differences here, which is plus 5, plus 5, plus 5, plus 5, plus 5. And that's just another way of writing it out if you don't want to use a formal table like we did in the question number 3. You could just write it out like that too if you are like me, short for space because you wrote in the way of making that table into a set of first differences. But we're going up by 5 each time, which again relates to our rate of change. And the third way to represent it was graphically. To do that, we have our I'll show you describe it in 2 ways. One, you have your table of values here, so you can just plot all your points. So we have 0 and 10 on my table of values, and again, I pre-made that table, and so I just went up this y column using these values here, and then my x column here. So again, we got 0 and 10, we got 1 and 15, 2 and 20, 3 and 25. Now we can also use our, let's finish that off, I guess, 4 and 30 and 5 and 35. But we can also use the formula to graph that. Our initial value is 10, so all we got to do is put a point here at 10. And then for every 1 I go over, because the rate of change is 5, or 5 over 1, as the rise over the run. Recall that the rate of change is rise over run. So I go a rise of 5, so from 10 to 15, and over a value of 1. And again, that's making that, let's use a different color here, that's making the rate triangle. So my rate triangle is up 5 and over 1, and that is the rate of change. So you can do that, and you can use that to kind of walk your way to each point as well. So you don't have to necessarily make a table of values if you're not asked to, but it is a very convenient way to do it, and then a good way to check and make sure you don't make any mistakes, especially when you get into the curved graphs that you'll be doing in grade 10. So there is 3 ways to represent that equation, that equation. So we got words, we got table of values, and we got the graph with, and I even illustrated the rate of change there using the rate triangle. Last 2 questions are 8 and 9, and so let's take a quick look at those. So in question number 8, we're just asked some basic questions about the Celsius and Fahrenheit conversions here. And so this is the equation that you can use to convert from Fahrenheit to Celsius. You take the temperature in Celsius, multiply it by 1.8, and then add 32 to that, and that will give you the change to Fahrenheit. So the first part, A here, says, what does the 1.8 represent? Well, in our case here, we're looking at a rate of change. So this is a rate of change. It's increasing by 1.8 for every degree Celsius. What does the 32 represent in part B? Well, that would be our initial value. So the 1.8 is our rate of change, our 32 is the initial value. Now the question says, what would the first differences be as the Celsius temperature increases by 1? So let's think back to the first differences we looked at in questions 3 and 4. In question number 4, as our time went up by 1, our values increased by 5 because 5 was the rate of change. So our first differences in this case were the rate of change. So when you're increasing by 1, then the first differences will be the rate of change. So in our case, for the temperature, the rate of change is 1.8, so the first differences would be 1.8. And now if we look back to the table where we did the hours and pay, when we went up by 5, the first differences increased by 5 times the rate of pay, which was $12.50. So we multiply by our increase here. So in this part D, what it says is, what would the first differences be and as the Celsius temperature increases by 2 degrees Celsius? So it's 1.8 for 1 degree, and so we just double that 1.8 and we would get 3.6. So for part D, the first differences, increasing the table by 2 degrees, the first differences would be 3.6 degrees Celsius. And then the last question here, number 9. We got Renato throws a ball into the air. The table shows the height of the ball at half-second intervals. Determine whether the relationship is linear or nonlinear and justify your answer. So what we need to do here is take a look at the values in the table. The times are going up by half a second, and that's fine. They're going up consistently. So we can compare the heights and look at the first differences. And if the first differences would be the same, then this would be a linear relationship. If the first differences are not the same, if they're not constant, it would be a nonlinear relationship. And looking at these values, without doing any calculations, already I can see, looking as it goes up in height, and then it starts going down in height, the first differences can't be the same, because the first differences are going to be positive numbers, and then all of a sudden they're going to be negative numbers at the end. And if you think about the path of a ball in the air, it's going to go up and then hit a peak and then go down, and it actually makes a kind of curved shape. It looks kind of like a stretched out arch when you throw it with a distance, but that same path that it follows as you throw, say you were to like an underhand toss a ball or something across the room, that arch that it follows, the change in height is the same even if you throw it straight up in the air. The way the time it takes for the height to change because of gravity. So what happens is the height is actually going to start going up, and then it's going to go up, however fast you throw it up, but then the gravity is going to slowly slow it down until it actually hits a point where there's actually a point where it stops and is not moving at all, and it's just for the briefest of instances before it comes down. So in this case here, knowing the situation, throwing a ball in the air is never going to be linear. It's going to be a quadratic type equation, and again, that'll be a grade 10 topic for you guys, so nonlinear equation. But just looking at the table of values as the ball goes up in height and then down, we are definitely in a nonlinear situation. So that about I believe that covered. Yeah, that's everything for our questions for this week. We have only a few more weeks left here. Got about 3 more weeks of videos, so we'll be looking at the algebraic equations as our last bit. So we're going to combine a couple of those topics into one video so that we can get through all of them. We got 5 more topics to cover. The linear relation content that we covered today, this is probably the most important stuff for you to remember moving into grade 10. If you can keep a handle on the concept of developing the tables and the first differences, understanding that, being able to read that equation and fill it into the table and graph it, and then determining the initial value and the rate of change portion, if you can do that stuff, you've covered. You got a good understanding of your linear relations, and that will give you a good foundation for grade 10. This is one of the major topics in grade 10 is you'll get into some work with linear relations. So make sure that you try and get this stuff understood, and that should give you a leg up moving into next year. Anyways, that's about it for today. So you take care, and we'll see you next week.